through this one. So for G2, I can identify key features of a graph and interpret their meanings in the context of a real-life scenario. Then the 4 application, I can sketch a graph showing key features given a description of the relationship between the variables. And just so that somebody doesn't let me forget, like I did today, this example here that we starred on the previous page, I do want to make sure we talk about that as a group because that's more an application. And then when we get to example 4 here, I think that's the example. Yeah. That's the 4 type problem for that one. So we're going to go over that together on Monday. All right, so our goal in this standard is to be able to work with any graphs, not just linear, and identify key points and use those key points to describe what's going on in the real-life scenario. So you will see linears, but you'll also see other types of algebraic functions, some that you might have never seen before. Okay, so key features or points. One of the key features, and this is what I call one of the most important points, is maximum or minimum. And they would be key points because of the fact that they are a maximum or a minimum. So usually it's telling us something very important about that situation. Another key point or points would be x-intercepts and y-intercepts. Okay, so for x-intercepts and y-intercepts, x-intercepts tell us where the y value is 0, depending on what y means, and the y-intercepts tell us where x is 0. And usually that's another important piece of information that we need to know or be able to interpret is what those values mean where x and y are 0. Other key features, a key feature would be the end behavior of a graph. This is where the graph ends up going. So like if you have an example like this, the end behavior on the left hand, you're going down towards negative values. On the right hand side, you're going up towards positive values forever and ever and ever. That usually tells us something about the function, that you'll increase forever this way, or you'll decrease forever this way, or vice versa. Okay, so end behavior of a graph is usually something that we pay attention to. And then the rise and fall of the graph. And we can kind of use this as the same example. But like what's happening here to make it decrease, and what's happening here to make it increase. Also notice those are maxes and mins. So these max and mins and x-intercepts and y-intercepts usually are where we start. We describe what that means. And then the end behavior and rise fall of the graph is where we kind of end up. And there might be some other key features that we add in later on. We'll see what we come across. All right. So I kind of made up these functions just to have something to talk through. For example 1, identifying key features. The following function models the rise and fall of a cow population at a particular farm. Identify the key features and interpret their meaning for this example. Okay, so we're going to use the tool at our disposal, which is our graphing calculator. I want you to go ahead and input, or if you don't have your own graphing calculator, just watch. I'm going to go ahead and graph this function. Well, actually, before we do that, let's talk about what x and y mean. X is your independent variable. Now, I don't give you much data here or much information about the situation, but I give you enough that we can make a good educated guess on what x and y could be here. Y is the population. Now, we can talk about maybe what y is reliant on, or if this is tracking the rise and fall of the population. It rises and falls based on some unit of time. So maybe we make x be months. I mean, you can make it be years, but some kind of time frame. And then the y is going to be the population. The argument here being that population would depend on some unit of time if it's rising and falling. Okay, so let's go back to our graph. I'm going to pick a standard graph here, so I'm going to go to Zoom. Standard, all that does is it sets up my window to be -10 to 10. And I'm going to go ahead and graph. Hello. Did I not graph it right? Negative 2x squared minus 5x plus 500. Okay, so this might be good that this happened. I don't see my graph at all. So I'm going to zoom out a little bit. Okay. I still don't see enough of it. Well, let's talk about something else. First of all, this is a quadratic. Hopefully from Algebra 1, you know that it's a quadratic that opens down because your a value is negative. Okay, so if we go back to our graph, I know this has to be a U-shaped curve. I see two of my most important points here, but I do know that there's at least a maximum somewhere in between. So I'm going to expand my y-axis up a little bit by going to my window. Maybe I go to 100. Oh, looks like I'm going to have to go more than that. Maybe let's go to 600, and the reason I go up to 600 is because this is a value of 500, so that might affect it a little bit. Oh, there we go. Okay, so I have a really good motion here. So let's go and find the most important points. Let's start with the x-intercept. To find this x-intercept, on our calculator we use something on the calculate menu. So we go to second and trace, and then we want the 0. A 0 is another name for x-intercept, so you're going to select that. And then ask the question left bound. Left bound just means this little cursor guy has to be somewhere to the left of where you know that x-intercept is. I know we lost track of it, but it just has to be somewhere to the left, so below it. Hit enter. Then it says right bound, so you have to be somewhere to the right, so anywhere above it. Then it says guess, hit enter one more time. And it shows my first x-intercept is at negative 17.11, and that gives me a y value of 0. So maybe I mark that. X-intercept, negative 17.11, comma 0. The y-intercept, oh, we'll find that because I have two x-intercepts. Let's find my other x-intercept again. Okay, so same thing, go to second and calculate. We want 0. Left bound on this x-intercept just has to be to the left. Hit enter. Somewhere to the right. Hit enter. Finds it at 14.61, comma 0. And then let's find the y-intercept here. Well, the y-intercept is a little bit easier to find. We can actually do this algebraically because the y-intercept happens where x is 0. So I actually can plug 0 in for x here, and if you do that, you end up getting 500. So that one I can do without graphing anything. Okay, so here are three most important points off of the important features here. Let's find my maximum, since I can see I have a maximum point. If you go to calculate, again, calculate menu. Left bound, you have to be somewhere to the left. Right bound, somewhere to the right. Hit enter one more time. And you're at negative 1.25. Comma 503.125. Okay, so there's my maximum point. Okay, we'll talk about the rise and falling here kind of in the description, but we're going to use our most important points here as a basis. Now remember that this models cow population, and the x-axis is in terms of months. So let's talk about where we start. If this is in terms of months, then really the only part of the graph that I want to pay attention to is this positive half of the graph because I can't have negative months. So any x values over here would really mean nothing in the context of my problem because I can't have negative time. It doesn't work.
I had to wait so long because he was doing stuff to your room. Oh. Down there it stopped letting people log in and get on the internet.
Okay. It's not working, and mine isn't working either, so.
I mean, I got
You got the gist?
gist of what we're doing right now.
Okay. Do you want to try some problems?
Sure.
Okay. I'm going to be talking because I'm like taping. Alright, so in this first half of the graph, if we start at where x equals 0, we saw that where x equals 0, I have 500. So in the context of the situation, I would start with a cow population of 500 cows. Okay, because that's where you would start as the months start ticking forward. Then the other x-intercept here that is on the positive side, because this is the one that really matters, and maybe we can even cross that out because that doesn't necessarily, well, yeah, we can kind of talk about that one. But let's talk about this one first. So it's 14.61. If 14.61 is what months represent, then what this is saying is that the population of the cows will be 0 at 14.61 months. So 14.61 months later, I have 0 cows. Okay. So the cow population decreased to nothing in a little over a year. You could make an argument that what this x-intercept over here means, this negative 17.11, we could say that 17 months prior to the decline, the population started and peaked, and that peaked word would refer to the maximum, peaked at 503 cows. Sorry, that's so tiny. Okay, so now that's going to be different. I mean, everybody's going to write a different paragraph, but what I would want to see is that you've identified what your x and your y could mean in context of the very short information that I've given you, that you've identified the x-intercept, the y-intercept, the other x-intercept, and a max if you have a quadratic, and then you've talked about each one of them somehow in your explanation and what it could refer to for this example. Now, as you start working on 4-type problems or actually other examples like this on Monday, you're going to get more feedback or a little bit more information. But if I don't give you very much information at all, you kind of have to extrapolate, which means take what you're given and kind of extend it past what you're given in order to give me a paragraph. But as long as you address each one and it's logical, then we're good to go. Okay, let's start at example 2. Go ahead and flip. This example, for example 2, we're going to go ahead and graph. This following function models the growth of bacteria after being exposed to air. Identify the key features and interpret their meaning in this example. So let's go back to y equals. We're going to do 3 times 4 to the x. Oops. Okay, I'm going to go back to a standard window here. Okay. Well, if you remember from Algebra 1, this is an exponential function. This one does not, like, what you can't see here is that this graph would continue to follow the x-axis forever and ever and ever because it's following what we call an asymptote. So it's like a fence that the graph cannot cross. And then what happens around here is something, whatever the function is representing, happens, and then it starts increasing very, very quickly. But let's identify some key features. I'm not going to have any x-intercepts because there's an asymptote. So maybe I even write that. No x-intercepts because there's an asymptote. I do have a y-intercept that I can see. And remember with y-intercept, it's like you're plugging 0 in for x. So if I plug 0 in for x here, 4 to the 0 is 1. 1 times 3 is 3. The other thing that we have not done yet that maybe we'll do over here is to identify what my x and my y mean. Okay, so we have the growth of bacteria after being exposed to air. I'm going to probably assume that the growth happens over time. So maybe X instead of months this time is minutes. And then the Y would be the amount of growth. Okay. Other key features, we are obviously increasing over time. So you can talk about, because your end behavior is going up towards positive infinity there. All right, and then maybe we'll write a little paragraph together because I don't see any max or mins happening there. Especially if you know the general functions graph. That's what an exponential normally looks like, so you know there's not going to be a maximum or a minimum. So pretty much all we have to start with is this y-intercept. So let's talk about what that y-intercept is. If your minutes is at 0, then that 3 represents the amount of growth when you start. So maybe you start with 3 bacteria. Okay, so I don't know if it's 3 pods or 3,000 or whatever, but we'll say we start with 3 bacteria. As your minutes increase, bacteria grows at a rate of. Now let's talk about what this rate is. And it's actually quadrupling every minute. And I know it's quadrupling because the base of my exponential is a 4. If this was a 2, it would be doubling. If it was a 3, it would be tripling. If it was a half, we'd have actually an exponential decay because every minute you go forward, it's halving itself. So in this case, we are growing at a rate of, we are grows, I don't know how to word that correctly. This is horrible English, but as minutes increase, the bacteria grows at a rate of quadrupling. Anyway, I think you get what I mean. So the window, just to kind of show what that means, if I was to plug in 1 here, so after 1 minute, I would have, let me write that here, other data. After 1 minute, I've increased to 12. After 2 minutes, 4 squared is 16. 16 times 3 is 48. You can see that for every minute you go forward, the y value increases by a factor of 4. And maybe that would have been a better way to explain this, is that it grows at a factor of 4 every unit of time. Okay, not as much we can write there because there's not as many data points to go off of, but that gets the point across here. Okay, and then I think that might be where we end up. Oh, we're a little past time. Sorry, I told you that was going to be a short one too. Sorry about that. Yeah, we'll pick up with example 3 on Monday and example 4. And example 4 is an example of the 4 that you have to do. And then we'll also do this